So after we've learned the standard form, basic solution, basic feasible solution, and then adjacent basic feasible solution, finally, I think we're ready to start learning simplex algorithm. So let's do it. So here are the steps in the simplex algorithm. The very first step is you convert the LP model into a standard form, which has been discussed in the first video of this week. The second step is try to obtain, if possible, a BFS from the standard form. And then in step 3, you ask this question, is this current BFS optimal or not? If optimal, you stop. If not, then you go to step 4. In step 4, basically what you're doing here is to obtain the adjacent BFS from the current BFS. How to do that? You will pick one non-basic variable to become basic variable. And then as a consequence, you will throw out one basic variable to become non-basic variable. So you do an exchange, you do a swap. One non-basic, you pick it to become basic, and then you throw away one basic to become non-basic. Don't worry if you don't catch this concept right away now at this moment. I will talk about this with much more detail later. And then after you determine the adjacent BFS, usually you will need to do elementary row operation to create the new BFS. So as you've seen in the previous video, these steps may be described with this flowchart. So the second step is obtain initial BFS. Step 3 is asking if the BFS is optimal. Step 4 is obtaining adjacent BFS and then perform the ERO, and then you go back to step 3 to ask the question, is the current BFS optimal or not? So that's really all the steps that you need to follow if you want to perform simplex algorithm. In the simplex algorithm, sometimes we talk about row 0. So row 0 is where we write down the objective function. So far, we usually write the objective function with this form that looks like this: z equals c1 times x1 plus c2 times x2 up to cn times xn. So the c here, there are constants, so numbers like 10x1 plus 3x2 plus 8x3 and so on. So this is how we usually write objective function. But in row 0 form, we will move all the terms that has variables to the left hand side. So you see now this x1, x2 up to xn, they are all in the left hand side, such that the sign now becomes negative because you move from the right hand side to the left hand side, right? And then what you leave on the right hand side is a constant. So z minus cx1 minus cx2 and so on equals 0. So this is the form that we called as the row 0 form. Let's perform simplex algorithm on this example. So Dakota Furniture Company manufactures desks, tables, and chairs. So we can say that x1 is the number of desks produced, x2 number of tables produced, x3 numbers of chairs produced. And then, as always, when you see the word requires something, it means this sentence is talking about constraint. And then you can see the requirement of resources for each product and then for every type of resource on this table. And then you can see also the availability of each resource. So it's also about the constraint. And then here sells for $60, $30, and $20. It must be talking about the objective function. And finally, there's a sentence with at most something. So again, it must be talking about the constraint. I will give you a pause on this video to give you the time to really read and understand this problem carefully. Okay, the very first step in simplex algorithm is to convert the model, the LP model, into a standard form. So for row 0, you just convert it into row 0 form, which means that you move all the terms with the variables to the left-hand side, and then on the right-hand side, you write down the constant. So the right-hand side is 0 because nothing left after you move all the terms 60x1, 30x2, 20x3 to the left-hand side. And then for the first constraint, because it is less than or equal to, you will add a slack variable plus S1, second constraint plus S2, third constraint plus S3, fourth constraint plus S4. And then finally, do not forget to write down that all slack variables, they must be greater than or equal to 0. So that's our standard form. We finished the first step in the simplex algorithm. Now let me introduce a new term, which is called canonical form. Our standard form from the previous slide is already in a canonical form because for each row in the equation that you have, or you can think about the constraint, you only have one variable with a coefficient 1 in that row and then coefficient 0 in all other equations. So let's take a look at the first row, the first equation or the first constraint. Here you have S1 with coefficient plus 1. However, S1 does not appear in all other equations. From row 0 to row 4, you do not have S1, right? Or if you really want to write S1, you can write it down like this, plus 0 S1. So this follow this definition above, coefficient 1 in that equation and 0 in all other equations. What about row 2? You have S2 that shows that kind of behavior. S2 has the coefficient 1 in row 2, but has coefficient 0 in all other equations. For the third equation, you have S3 that shows such behavior. And then for the fourth equation, you have S4. For row 0, you actually have Z that appears here with the coefficient 1, and then it does not appear at all in other equations. So this is already in a canonical form. What can we interpret or get from a canonical form? You can say that those who are not in the canonical form, x1, x2, x3, they are non-basic variables. Those variables who are in the canonical form, s1, s2, s3, and s4, they are the basic variable. If you look at the textbook, sometimes it also write down z in the column of basic variable, but when we talk about basic variable, usually we only care about the variables that are not z variable. Okay, so that's about canonical form, and then the information that we can get from the canonical form is that which variables are basic variables and which variables are non-basic variables. Based on that information from the previous slide, now you know that you have obtained a BFS. And why it is the case? Well, because you have all variables here, they are all greater than or equal to 0. And then these S1, S2, S3, and S4, they are your basic variables. And then how do you know that X1, X2, X3, they're all 0? Well, because they are all non-basic variables. That's why the value of X1, X2, and X3, they are all equal 0. So you have obtained a BFS, and that means you have completed the step 2 in the simplex algorithm. Sometimes you will see that we represent a solution using the table that looks like this. So the title of the column are the name of the variables, and then the coefficients and the constants you write down below the corresponding column. So this is the representation that we usually use because we do not want to keep repeating writing like minus 60x1, 8x1, 4x1, 2x1. So we just put the name of the variable as the title of the column. I will discuss step 3 of the simplex algorithm and step 4, step 5 in the next video. So right now I just want to give you some questions to check your understanding about what we've discussed so far. So in the Dakota problem, given the decision variables, given the BFS here, and then each of this corresponds to a particular constraint in the Dakota problem, there is a statement saying that in this solution, Dakota produces 0 desks, 0 tables, and 0 chairs. Is this statement true or false? The answer is true, because in this solution x1, x2, x3, they are non-basic variables, so the values of those variables are 0. Remember that these are your basic variables, s1, s2, s3, and s4. They have values, but x1, x2, x3, the values all equal 0. The second question, in this solution, S3 is a basic variable and the value is 8. So S3 equals 8. It means that Dakota uses 8 hours of carpentry in this solution. Is this true or false? Well, the answer is false. So S3 is a basic variable. Yes, it's true up to this point. S3 equals 8. Yes, it is true up to this point. You can see here S3 is a basic variable and the value is 8. So up to this point it is true. But remember that slack variable means that the resource that is unused. So it means that in this solution we have 8 hours of carpentry that is not used. And then if you think about this logically, here x1, x2, x3, they are all equal 0. So we don't produce desk, we don't produce table, we don't produce chair. So obviously we will not use any resource either, right? So it doesn't make sense if you say Dakota uses 8 hours of carpentry because Dakota does not produce anything. So it shouldn't use any resource. So that's the end of this part 1 of the simplex algorithm. We have so far discussed step 1 and step 2. In the next video, we are going to look at step 3, 4, and 5. So see you in the next one. Thank you.